Hey guys, Arun here. I'm super excited to announce my next contest to you. Shall we play a quick game? What if I challenged you that the whole of mathematics so far, standards 1 to 12 that is needed for engineering, would only take 30 minutes to explain? Just 30 minutes. Would you believe me and accept the challenge? To help you, I'm going to give it a shot, guys. Under 30 minutes in 5 audios. Send us your audio recording by December 2nd. The top 5 expressions will be selected to become my ambassadors of all subsequent engagements with SVC. There is one more bonus if you are an art lover. Check out the next page. Top 3 artistic models will get a bonus opportunity to get super creative with robots. Good luck. Here is my first 6 minutes. Where does mathematics start? Counting. You started counting sheep, goats, 1, 2, 3, 4. When it came to 9, you wondered what to do. 0 came in, so you added 10, and then you went 20, 30, 40, 100. The decimal system was fantastic. Visualize a number line right now. Think of going right in the number line as you count more and more. Every time you count something more, you're going right. And sometimes you just don't go one step, you jump count. If you go 2 steps at a time, you're multiplying. If you go 10 steps at a time, you're multiplying by 10. That's how you go faster and faster in the number line to the right hand side. What about negatives? Sometimes you have to give away stuff. You go in the opposite direction. You change the direction and you go left hand side in the number line. Visualize this. This comes very handy. What happens when you divide? You are dividing things into equal groups. You decide how many people are there and how many objects are there, and you divide it equally and you give it to people. The most important thing is every group gets equal quantities. That's the concept behind division. So you might put x divided by y, 10 divided by 5, 9 divided by 3 and what not. The concept is, the result is equal proportion that is received by every person. That is the division. Now comes fraction. Not everything is completely divisible by another number. 1 divided by 2, you need to make it into a fraction. 0.5. What if this 2 was more? You have to divide 1 apple among 10 people, 20 people, 30 people. The denominator keeps getting bigger and bigger. The fraction size keeps reducing. Another way to represent it, decimals. 0 point, not, blah, blah, blah. You get the real number space. From integers, you slowly moved into something that is real, which means a number could have infinite decimals, could have finite terminating decimals. Then the concept of infinity is coming up, which is between two numbers, between any two numbers. How many numbers are possible? Let's just pick 1 and 2. Between 1 and 2, how many numbers are possible? A kid would say 2.5 and 3, just 0.5, that's it. But you would say there is infinite numbers between two numbers. Now comes the concept of exponents. You want to grow faster between one number to another number. What would you do? You were bored of multiplication. You scaled it, but you were not happy about the size at which you grew. So you become exponents, which is you have a base and you raise it to a specific number. 2 to the power of 3, which is multiplying 2 by itself 3 times. 10 to the power of 20, which is multiplying 10 by itself 20 times. And so on and so forth. What is logarithms? Logarithms is exactly like exponents, but somebody wants you to reduce a bigger number to a smaller number, considering that you have another base to which you have raised this new number. Logarithms and exponents are 100% identical. And what happens when you raise a number to a negative number? You make it smaller and smaller. The number actually shrinks. And when you do in terms of logarithms, you get into the negative logarithms as well. What happens when you raise a number to a fraction? Let's say 0.5. That is nothing but a radical. You're making a square root. So exponents, logarithms and radicals, even though they have 3 different conventions, you write a to the power of b, you write log of a to base b, you write eighth root of b. All three mean the same. Take a moment and think about it. There is no reason for these three things to be represented in three different ways. Now comes the concept of functions and variables. What is a function? What is a variable? So far we've talked only constants, which is numbers. It could be real, integers, positive, negative, one raised to another, one logarithmic base of another, so on and so forth. But what if we had to talk about something that could change? Something is there today and it could change to something else tomorrow, and you still want to do nice mathematics with it. You would do algebra. You would bring in a variable called x and you will call it 5 today. You will perform a lot of operations with it: x squared, x by 5, 5x plus 4, 3x plus 5. These are all called expressions with the variable called x. And you make equations with it when you have a left hand side and a right hand side for that expression. Why is xy plot important now? When a variable moves, how is it changing? Is it changing really fast with respect to another variable? Because you have an equation now. Is it growing fast? Is it growing less? Is it growing faster than something else? So a visual representation of variable is extremely important. That's where you understand when functions grow really fast, when they will grow really slow. Consider all the previous points: negatives, fractions, real numbers, exponents, logarithms, in the context of variables and how they change over the xy plot. So that gives a good intuition of our first section. Okay, here comes my second 6 minutes. If we've talked about numbers so far, variables, exponents, logarithms, real number space, and just started to visualize numbers in the xy plane. When it changed, when some variable was moving, we started to visualize this. Now comes shapes. You can make geometric shapes out of these visualizations. You draw a square, yes, it has all equal sides. A rectangle, it has two equal sides, different shapes, quadrilateral, so on and so forth. They are all results of something changing in two dimensions, x and y. What happens to the circle? What is a circle? You start with a single point and you draw equal radius around it and you draw a circle. It is still not perfect. A circle is a beautiful imperfect figure which has a circumference of 2 pi r, which can never terminate. Pi, remember, is an indefinite number, so 2 pi r can never terminate. So every circle that you are seeing is actually an imperfect approximation. Why are you going around the circle and saying that you've covered 360 degrees? Where did the number 360 come from? Why not 400? Why not 500? The sun is at the center, the earth is going around the sun. It took roughly 365 days to come back to the same place. Olden days, they did not have accurate ways to measure, so they approximated it to 360 so they can conveniently divide it by 4 and make it into quadrants and so on and so forth. 360, that's where it started. That is the degrees measured from the sun as the observer of observing the earth. Every day it would go 1 degree. What is radiance? Radiance is from the earth itself. Earth is moving around in a circle. If you allowed it to move r distance along the circle, then it would do 2 pi times r to go and come back to the same place, because 2 pi r. So that r distance that it covers along the circle is the radiance. So radians and degrees are therefore two equivalent ways of representing angles. Now comes when you have three angles in a shape, it's triangle. Could be of different combinations. Geometric constructions are possible. You take circles, you take a compass, scale, you can do wonders with it. But the most fundamental triangle is a Pythagorean triangle, which has a 90 degree. So sum of the squares of the two sides would become the square of the hypotenuse. This can be proved. The area of a triangle is half into base into height, again can be proved. Divide the rectangle into 2, base into height, and that's half of it is the area of the triangle. Understand why does a specific formula gets injected very early into you. you should be able to prove most of these. Now you visualize these shapes right now, you got a good understanding of angles and how triangle is formed. Now you're slowly moving to equations that is formed from these visualizations. What equations can be formed? X squared is nothing but a square shape with side of x. So when somebody says, hey, this is x, how will you square it? You should not say, hey, what is the value of x and this is how you square it. You should say, if you want me to square x, I would draw a square of side x and make it a perfect square. Okay, so now if I were to make xy, how will I show it? I would draw a rectangle of x length and y breadth. So xy, it's a product. That is how I form areas. So areas or representations of properties of shapes itself come from algebra and visualizing algebra in the two-dimensional space. And that's the beauty of where algebra connects to geometry. The next step is your understanding how these triangles properties are very proportional when there is a right angle involved. Why would the ratio of opposite side by hypotenuse remain the same irrespective of how big you grow the triangle, keeping the same theta? Then that is the sine theta. If you do the same thing with adjacent side by hypotenuse, no matter how big or small you make the triangle, the ratio remains the same, that is cos theta. Why would it remain the same? It's an amazing property. To understand this better, you would draw a unit circle which is x-axis and y-axis. At the center, you will make sure that the circle is rounded with unit radius. You go around the circle, you're covering radians. If you go around the circle and come back to the same place, you're covering 2 pi radians. And when you do that, you measure the opposite side by hypotenuse. Hypotenuse remains 1, so the sine wave is beautifully negotiated when you go around the circle. And now comes the concept of polynomials. Why are polynomials important? You're visualizing just not geometric shapes, you're trying to think about what happens when the degree of a particular variable is slowly increased, how the different shapes are getting formed in the two-dimensional space, and when does it cut the x-axis, when does it cut the y-axis. You're trying to understand if there is a straight line, there is a slope involved, how do you represent the equation of a line. These equations mean everything in the two-dimensional space. They are just not equations, but every time you put a variable and you constrain it to an expression, you are giving a lot of meaning to it. And the polynomials, the coefficients of the polynomials also play a large role in how these shapes turn out to be. So here is my next 6 minutes. So far we've covered counting, understanding of negative numbers, fractions, real numbers, infinity between two numbers, exponents, logarithms, and understanding the visual representation of algebra, geometric shapes, concept behind triangles and circle, and so on and so forth. Now all these naturally lead us to what happens when a variable changes or multiple variables changes in our real world. Right now as I speak, the time changes, the temperature in the room changes, the speed of the fan changes, so on and so forth. Now this all presents us with a lot of data, so an understanding of statistics becomes important. In statistics, there are useful metrics such as average value that is possible, the most common value that is possible, or the median, or the mode, or the variance from the mean, or standard deviation, so on and so forth. These are not just formula, but they have an additional meaning. They are trying to convey you, crunch you the data and give you a key metric that you will use to solve specific problems, such as following. What is the probability of a certain event occurring that is closely connected to this particular statistics? The number of possible outcomes have a reflection towards what is the most likely outcome that is possible, or how likely is a certain event possible to be favorable, not just for gambling but to make most business decisions. This is a very useful metric. Random variables, you associate them to a limited subset or a set of spaces and you distribute them over another function. You treat a probability as a function and you enjoy how it changes over multiple dimensions. When dimensions come, vectors naturally come together, because vectors are nothing but I, j, k or x, y, z are the amount of growth or reduction possible across multiple dimensions. And why matrices are useful here is because you perform vector operations like solving a particular equation or understanding the statistics using multiple dimensions. You can use digital hardware to simplify these computations, multiply, accumulate, therefore matrices become important. Naturally leads us to studying change. When a particular dimension there is a change, what happens? You study calculus. In calculus, you are worried about an instantaneous change of a certain phenomenon. The best way to understand calculus is to think about physics. In physics, an object, let's say stationary, its displacement is zero. It is not moving at all. Now, what happens to its velocity is the rate of change of displacement. You do ds by dt, it is also zero. It is not changing. Let's say this displacement was at a constant place 5 units from the origin. You are not changing the velocity at all. What happens to acceleration, which is the second derivative of velocity, which is also zero? Now, on the contrary, when there is constant velocity, when there is a uniform velocity or a specific number, let's say 3 meters per second, draw an x-axis and a y-axis. In the plot velocity, mark 3 and draw a straight line parallel to x-axis. Now understand, draw the equivalent graph for displacement. You see that there is a uniform distance will be changing because the object is not stationary anymore. It has a uniform velocity, so the distance will change uniformly. It will be a straight line going through the origin and it will have the slope of that particular velocity. The slope of the displacement curve against time is same as the value of velocity that you originally started with. And what is the acceleration? Now you have a uniform velocity, so there is going to be no acceleration. So if you differentiate that, you will get 0. Now go reverse again. Let's assume that there is an acceleration, a uniform acceleration of 9.8 meters per second squared towards Earth. So you draw a line, you draw x and y axis. X axis is time, y axis is acceleration, 9.8, draw a line parallel to it. Now figure out what would be my velocity change. It would change 9.8 per the slope of 9.8. So every second there is going to be an increase in velocity of 9.8. And how will therefore my displacement look? Parabolic. That is where your half at squared comes. So s is equal to ut plus half at squared should not be a formula introduced to you when you are in 6th standard or 7th standard. It is when you beautifully understand how calculus brings this parabolic effect of constant acceleration to a uniform sloped velocity to a parabolic increase in distance as time goes. That's the beauty of calculus. Now, what is integration? You actually do the reverse of this. You accumulate small changes of displacement, small changes in velocity, you will come to displacement. So you integrate velocity, you will get displacement. You integrate acceleration, you will get velocity. It is nothing but you are accumulating small changes of what is happening instantaneously to arrive at the original variable. Trigonometric calculations often have calculus in them because they are easy to solve. They have equal growth in two directions, positive and negative, so they cancel out. They are very easy to solve, so you'll find them often in trigonometric equations. So far we've enjoyed mathematics from basic counting to calculus, just counting 0, 1, 2, 3 all the way to studying change, visualizing it in 2-dimensional, 3-dimensional space with matrices, vectors, understanding statistics, probability, trigonometric equations, everything. Now it's time to understand certain constants. We'll start with pi, which is the ratio of circumference of any circle, small or big, by its own diameter. This has confused so many people in the past. They were all trying to figure out what is the best expression for pi. Where will it end, and will it end at all? And you have any circle, this ratio of circumference to diameter was pi, and this was enough to prove that any circle that you're drawing right now is imperfect. It is just an approximation, because 2 pi r, you can never complete that circle and say this is 2 pi r, right? So now the next number that we'll introduce, the next constant that we'll introduce is e. E is a special number which is nothing but interest. What is this constant called 2.71 blah blah? It is compound interest. Why should you raise e to the power of something and say e to the power of 5, e to the power of pi, this, that? Is because this particular number has a special property that if you start with 1 rupee and you accumulate interest over it, let's say for 1 year, saying 100%, you would have to give back 2 rupees. So 2 has come, but 2 is just not enough. If you say that only 6 months I'm going to give you back your 1 rupee, what is the new interest rate? And if the loan guy says it's 50%, then you're saying that 1.5 you might be fine, you would have given it back in 6 months and you're happy. But let's say you did not, you compounded to 0.75 plus 1.5, it would become 2.25 while it was just 2. It became worse. And will it get worse further if you were doing this compound interest every month divided by 12, which is 8%, or every day, which is divided by 365, so on and so forth? If you did it all the way to microsecond, millisecond, if you compounded for this 1 rupee, you would end up with this magical number called E. And mathematically expressed as compound interest is 1 plus 1 divided by n to the power of n. As n tends to infinity, it trends towards this magical number called E. To understand why you are raising this to another number called pi, 2 pi, we have to understand complex space a little bit better. What is complex numbers? Square root of minus 1 does not have a real value, so you dedicate it as a new constant called I. I squared is minus 1, alright. I to the power of 3 is minus I, alright. I to the power of 4 is 1, but why? Where is this I coming from? I is nothing but you are rotating a specific vector along the y-axis by 90 degrees. You're rotating, I shouldn't say by y-axis, but rotating it by 90 degrees. Let's assume x-axis to be real and y-axis to be imaginary. And visualize a unit circle which passes through the points 1 in the real plane, I in the imaginary plane in the y-axis, minus 1 in the x-axis, and minus I in the y-axis imaginary plane. You are going around the circle, you are multiplying by I. From 1 you went to I, you just rotated by 90 degrees, and you further rotated by 90 degrees again, you came to minus 1 in the real plane, and you rotate by I again, which is multiplied by I, you get to minus I, and then you come back to 1. This is extremely useful when you do signal processing and Fourier series understanding in the next videos. So now, where is this pi and 2 pi coming with this I is because your 2 pi radians make 360 degrees, which is one rotation all around this beautiful unit circles. Next is, when you talk about pi, you say it is infinite, but has anyone ever given an expression for it? Look up on Google who gave the first expression for pi. It's Madhava series, also called Leibniz series, within brackets 300 years later, is an expression of pi, the first beautiful expression of pi. Who conquered infinity to give this is Madhava of Sangamagrama, which is in Wikipedia today. So now, which brings us to the point that even when you add things to infinity, 1 minus 1 by 3 plus 1 by 5 plus dot 1 by 1 factorial, this, that, and everything to dot, certain series converge, and there could be mathematical tricks done to prove that these converge to specific values, which could be extremely useful. From there on, we are jumping to a beautiful concept of Euler's formula, which serves as the foundation Fourier series. What is Euler's formula? E is the number that we constant that we talked about to the power of 2 pi I. 2 pi I, which means you're rotating in the complex plane, you're growing from 1 to E 2 pi times fast, certain times very fast. E is a special number. E to the power of 2 is twice as fast as E. You're going from 1 to E twice as fast, thrice as fast. So 2 pi I as fast is rotating along a new plane, and you've come back to -1. That's the beauty of these Euler's formula. So now it would start to make sense why the complex plane is important, where E, pi and I are doing this beautiful magic for you. Alright guys, the moment has finally arrived, and I'm going to explain Fourier transform for you now. Believe me, if you get this Fourier transform clicked in your brain right now, whole of your engineering and further education will become an absolute smooth sail, because this is one of the most profound insights made in advanced mathematics connecting to engineering. From now onwards, any equation that you see, you will be able to appreciate it beautifully if you get this clicked. But let me caution you, it will take multiple revisions for you to understand this entirely. You will have to hear all the previous 4 series, and I hope you are ready now to absorb Fourier transform. Here we go. Fundamentally, what is Fourier transform? You have any signal. I am speaking to you right now through voice. I'm disturbing the air molecules around my mouth with my vocal cord to create a specific sound pattern. Therefore, a frequency emerges from my mouth. Just not one frequency, but I'm modulating, I'm changing my voice, and so that I can speak words. So there are multiple frequencies coming at different points of time to help you make sense of what I'm saying right now. And how is this getting recorded into the microphone? There is an analog to digital converter. Before that, a transducer that actually understands this air molecule movement and converts it into analog signals to even make it convertible into digital. That is when analog to digital signal conversion happens. So now, all that said, you cannot store this voice as air molecules moving left and right, and it is impossible to store it inside a phone. You can store it as a function of frequencies. Now, this smart man called Fourier, he presented this idea, and this stayed apparently so for more than 100 years, that any time-based signal, what is a signal? Right now, time-based change of my voice is amplitude, frequency, lot of things are changing with respect to the time, because I'm recording this audio only for 6 minutes. So within the 6 minutes, if you notice, my amplitude of the signals will be drastically different. My frequency that I pick, because when I shrill my voice out or when I go low frequency, there are so many things are changing. So this is the period of window in which my signal is changing. What did Fourier say? He said you can take out all the frequencies away from this particular time window if you could intelligently understand the pattern behind it. There is a pattern behind it, and if you can intelligently understand it, you can take out all the frequencies, and by selecting only the top 20, 100 few frequencies, you can completely reconstruct the signal, and therefore you can store it inside your phone, send it over the internet, and do everything with it. And it just not applies to voice, believe me or not, applies to images, applies to heat transfer and whatnot, and everything in this world can be modeled by this beautiful phenomenon. What is at the core of it is, how can a signal be represented? Frequency, what is all these frequencies, right? Frequency is cycles per second. Changes in amplitude, changes per second is frequency. Higher, lot of changes per second, high the frequency. Less changes per second, lower the frequency. Why is frequency important? You are trying to model the rate of change using this entity called frequency. How is it connected to your imaginary real plane and the circle in trigonometry? Is how fast you go around this circle producing these sine waves can determine what is the frequency at which this particular signal is getting propagated. You can go really fast, you are actually producing a high frequency signal. You go really slow around the circle, you are producing a low frequency signal. And can you add multiple speeds? Therefore, can you add multiple sine waves to produce new waves? Yes. Fourier proved that any signal can be represented as a sum of sinusoids given with a specific amplitude chosen so that they cancel out at times when you do not need them, and they will add to whatever you want when you need them, and that is the beauty of Fourier transform. இது புரியலைன்னா திருப்பி இதை கேட்கணும், ப்ளஸ் இந்த லிங்கை பார்க்கணும். பார்த்தாக்கா you will have a clicking moment when you will understand that hey, any signal has a periodicity and you can start any signal at a relative point so that it correctly adds together constructively at a specific point all the sine waves, and they cancel out when you don't need it, and the magic of the Euler's formula comes into picture. The cosinusoid, the sinusoids come into picture, cos theta plus I sin theta comes into picture and does this magic for you that a signal can be represented in this form. Once it is represented as a summation, இதுக்கப்புறம் பாலினாமியல் பூந்து விளையாடிடலாம், Fourier transform கண்டுபிடிக்கலாம், discrete Fourier transform you can find, you can enjoy fast Fourier transforms and many other transformations which are all possible in engineering. I hope it gave you an intuition, and I'm really excited by the videos that you will record and the contest that's going to go on from now onwards. Good luck, guys.